Have you ever faced a programming challenge that just seemed impossible to solve? It can be really frustrating, right? If you're struggling with subarray queries, you're in the right place. Today, we're going to break down this problem and find a solution together. I totally get it. Trying to sum elements in an array based on specific conditions can feel overwhelming, especially when you're dealing with large data sets. You're definitely not alone in this struggle. Many programmers face similar challenges. Let's dive into the specific question at hand. One user asked, how can I efficiently sum elements in an array between two indices that are less than or equal to a given value? They provided an example with an array and multiple queries. Sound familiar? Let's explore this together. So what makes this problem tricky? The challenge lies in efficiently processing multiple queries on potentially large arrays. The user mentioned using Moe's algorithm and a binary index tree, but it seems that the performance isn't quite where they need it to be. Let's break down the issue. And stick around. By the end of this video, I'll share a potential solution that could significantly improve your algorithm's performance. To improve the performance of the solution, the user can consider using a segment tree with a modification to handle range queries efficiently. This data structure allows for quick updates and queries. The user should implement a segment tree where each node stores a sorted list of elements. This will enable binary search to quickly find elements less than or equal to a given value. Next, for each query, the user can retrieve the relevant segment of the tree and perform a binary search to find the sum of elements that meet the criteria. This approach reduces the time complexity significantly. The user can expect a complexity of O log n for updates and O log n for queries, making it much faster than the previous method. Finally, the user should test the implementation with various queries to ensure accuracy and efficiency. This will help confirm that the new approach works as intended. Fun fact, did you know that the concept of algorithms dates back to ancient times? The word algorithm is derived from the name of a Persian mathematician, Al-Khwarizmi. Talk about a legacy. Now, let's look at the answers provided by other users. An alternative approach suggests decomposing the problem differently by building a tree of half arrays. Each subarray is sorted, and a cumulative sum array is created for efficient querying. For each query, you can decompose the interval into binary subintervals. This allows you to find the sum for each part separately and then combine the results. The initial tree building can be done in O n log n by sorting pairs of values and indices, then populating the tree nodes efficiently. Let's take a look at an answer from another user. An alternative approach to solving the subarray queries involves several key steps. First, sort the queries based on the value of C. Next, sort the array values in non-decreasing order. Then maintain a data structure like a binary index tree or a segment tree to store the range sum. Before answering each query, update the indices of all array elements that are less than or equal to C. Finally, answer the range sum query. This method has a time complexity of n plus q, all multiplied by log n, and a space complexity of on. Here's a pro tip. Always analyze the complexity of your algorithms. Understanding the time and space complexity can help you choose the right approach for your problem. And there you have it. With these strategies, you should be able to tackle subarray queries more efficiently. Remember, experimenting with different data structures can lead to better performance. If you found this video helpful, don't forget to subscribe for more programming tips and tricks.